Welcome to the virtual demonstration of the SITOP PSU8600 power supply system. The demonstration software was programmed in HTML5 and runs on all the usual browsers. This first video will give you an overview of the simulated application. In this application, the SITOP PSU8600 power supply system is completely embedded in totally integrated automation. The PSU8600 can also openly communicate with other automation systems via Industrial Ethernet in OPC UA. However, here we show the integration in TIA, controlled by the SIMATIC S7-1500 PLC with the CPU 1513 and the SM523 digital input-output module. We are using a 15-inch SIMATIC IPC477E for visualization and data processing. The power supply can be very simply configured through the TIA portal and integrated in the Profinet network. We are using the 3-phase PSU8600 basic device with a rated output current of 40 amps. It has 4 10-ampere outputs that are monitored for overload, which makes it a very compact solution with integrated selective protection. The basic device can be expanded to include various modules via this connector, known as the system click link. For instance, it can be used to expand the system to include up to 32 additional outputs, or to transform the power supply into a full-fledged DC UPS. In this application, the only additional module is the BUF 8600 4 seconds 40 amp buffer module. If the power fails, the integrated double-layer capacitors, called ultracaps, provide a load current of up to 40 amps for 4 seconds. Pre-configured WinCC faceplates are used for visualization. The faceplates for the PSU8600 are available at no charge. You can see the status of the basic device and the most important values at a glance on the PSU8600 faceplate: the operating status, the input voltage along with the voltage, and current values for each output. The system load current is the sum of all output currents. Under Information, you can also see the serial number and the firmware status of the SITOP PSU8600. Under Trends, you can see the output current characteristic for each output. We have integrated a static graphic for our demonstration. Of course, in reality, this is dynamic and provides information about the behavior of the connected loads. The other faceplates are used for the subsequent simulation runs. We simulate faults such as short circuits and various overload states in the control circuit. We also simulate power failures. We review some of the special functions of the PSU8600. These include the ability to adjust the output voltage, for example, to control a fan. We demonstrate how outputs can be completely switched off, for instance, using Profi Energy, available as part of the Profinet functionality, to save energy in non-operational periods. In the next video sequence, we show the switch-on process, the response of the PSU8600s to faults, and the possibility of identifying pending faults. Keyword: predictive maintenance. You switch on the application here. When switching on, take a look at the individual outputs. They are switched on sequentially, one after the other. Various delay times can be set for the PSU8600. 0 milliseconds, which means simultaneously, 25 milliseconds, 100 milliseconds, and load optimized. Load optimized means that an output is only switched on if the previous output has again fallen below the set threshold value. Using sequential switch on, the total inrush current is reduced and the load on the power supply is reduced. The power supply, control and the IPC are now connected through Profinet, and the application is up and running. Let's first take a look at what happens when a 24-volt feeder develops a short circuit. I briefly short-circuit the lamp, and output 2 of the PSU8600 is immediately shut down, All the other outputs remain unaffected. This means that the output voltages remain stable and the control continues to operate. We can see the fault message relating to output 2 in the S7-1500 display. The fault message is also output in the alarms faceplate. Alarm messages can be cleared using this orange reset field. We can see the status of the output with the associated text in the PSU8600 outputs faceplate. If the short circuit was removed, then the output can be reset again at various locations, which means that it can be activated again. For instance, on the faceplate here at the output, using the common reset, using the remote reset button, or directly at the device using the LED push button of the output. I reset the output from this faceplate. We now simulate two different overload states at this 24-volt drive. However, first I would like to say something about the setpoint values that have been set, which we have specified here. In the normal state, a current of 2 ampere flows. We have set 2.5 ampere as threshold value I set of the fourth output. If this value is exceeded, and it is not exceeded by more than 50%, then the output is shut down after 5 seconds. If the increase exceeds 50%, which means above 3.75 amp, then the output is immediately shut down. We already saw this effect for the short circuit that we deliberately caused. In the PLC program, we also set an even lower threshold value of 2.2 ampere. This represents about 90% of shutdown current I set. This means that an alarm is output for a current above this value, I-alarm. However, the channel is still not shut down. Let's now talk about overload. If I set the switch to low overload, the motor current increases to 2.3 ampere, exceeding the alarm threshold of 2.2 ampere, and the PLC program outputs an alarm message. Based on this information, the company operating the plant or machine troubleshoot the situation before the output is immediately shut down due to overload and the plant or system grinds to a halt. A foreign body may have blocked the drive or a bearing run dry. The warning threshold allows the operator to carry out preventive maintenance of his machine, therefore possibly avoiding any production downtime. If the overload situation is already critical, it goes without saying that the output must be shut down in order to avoid more significant damage. We simulate this using the critical overload switch position. The load current increases to 2.9 ampere and is therefore above the set threshold value of 2.5 ampere. After 5 seconds, the output is shut down and an alarm message is automatically output. Just the same as for the previous short circuit, the alarm is shown in the S7-1500 CPU display and in various faceplates, for instance, here in the overview or under alarms. Once the fault has been resolved, I can reset the fourth output again, either via the faceplate, remote reset, or the PSU8600 itself. I now use the common reset. The voltage of each PSU8600 output can be individually set. A voltage between 5 and 28 volt can be set using the potentiometer, and between 4 and 28 volt using the software. The voltage can also be dynamically changed in operation. And this is precisely what we demonstrate here using a fan at output 3. I can continuously adjust the output voltage using the slider. In the faceplate, we can see how the voltage and the output current changes at the PSU8600 continuously measures them. The voltage can also be specified using this editor. I enter 18 volt and confirm this using this check mark. If I attempt to enter a value outside the possible voltage range, then the lowest or the highest possible value is automatically set. I enter a very high value, acknowledge it, but 28 volt is automatically set. I now enter 0 volt, but 4 volt is automatically set. In other words, you cannot enter a wrong setting. If you really do want 0 volt at the output, then this is possible by shutting down the output. The output can be manually shut down directly at the device itself. The output LED of the PSU8600 is lit, and the corresponding fields in the faceplate turn yellow. If the output is switched off at the device, then it can only be switched on again from here. This is for safety reasons, so that an output is not switched on that was, for example, consciously switched off for commissioning. A remote reset via push button or faceplate is not possible. The outputs can also be switched off and switched on again using the software. For this application, we implemented this using these on-off fields. The field and the output LED then flash red. We can remotely switch on an output from various faceplates. If an output was shut down from the faceplate, it cannot be switched on again at the device, but only using the software. The SITOP PSU8600 power supply system offers some specific options for implementing energy management in the overall system. The power supply system always saves a lot of energy because it has a high efficiency of 94%. It differs from conventional power supplies as a result of two special features. One feature is that outputs can be specifically shut down, and the other is that the voltage and current of each output are sensed. Continuously measuring voltage and current ensures that the energy flow in the complete control circuit is transparent. Based on this transparency, for example, the increased energy consumption of a faulty load or consumer can be identified, for instance, as a result of an overload, as in the case of our motor. Our demonstration also shows how you can save energy by shutting down large consumers without completely running down the system. Using Profi Energy, part of the Profinet functionality, we can identify which outputs should be shut down during the non-operational period. Outputs 2 to 4 are shut down in our demonstration. I now press on pause and we can see that the only first output for the PLC and the IPC remain active. The demonstration has automatically switched over to the energy management faceplate. As default setting, the demonstration has a pause time of 10 seconds. However, we can change this using the editor and start the pause from the faceplate. Here we can see how long the pause will still last. We can exit pause prematurely by pressing stop. It is important to mention Power Display P. Only 52 watts is required in the pause, as only the first output is active. The power increases if the other three outputs are switched on again. As you can see, this is about 120 watts. If we now increase the fan speed by increasing the voltage, then we can clearly see how the power consumption also rises. And if we bring the motor into an overload condition, then of course the power increases as well. Using the PSU8600, we can also sense the energy that it required during operation. Because this doesn't make too much sense in this demonstration and would also be quite time-consuming, we are only showing a fixed value here. The basic device was expanded to include a BUF 8600 buffer module, which can maintain an output current of up to 40 amps for 4 seconds. We could also operate the UPS 8600 DC UPS with battery modules, which would mean that the buffer time would be naturally a lot longer. However, the BUF 8600 is equipped with ultra caps, which is sufficient to demonstrate the principle of operation of the power supply system when the power fails. To start, we simulate a brief power failure using this red button. After 3 seconds, we see how the operating mode switches over from line to buffer operation. The application continues to operate without any interruption. The demonstration automatically switched over to the BUF 8600 faceplate. We can see the charge state of the buffer module here. I repeat the brief power failure, and we can see that the buffer module discharges to approximately 60% until the line voltage returns and the capacitors charge up again. The BUF 8600 charges up again relatively quickly in order to buffer additional power failures on the DC side. Finally, we switch off the application using the knob switch. We then see a process that also happens for longer power failures. I will explain it in advance so that it is easier to understand. In the first 3 seconds, the system responds just the same as for a brief power failure. All 4 outputs are buffered. Outputs 2 to 4 are then shut down so that the remaining energy of the power buffer module is available for the important first output. This priority assignment is automatically realized in the default setting if the buffer module has been discharged to 50%. This means that there is sufficient time to save the data of the industrial PC and to cleanly close the application in a controlled fashion. The first output goes into a no voltage condition and the S7-1500 switches off only after the IPC has cleanly run down. I now switch off the power. All outputs are buffered for 4 seconds and then only output 1. Data is saved and the IPC is run down in a controlled fashion. Output 1 and the PLC are switched off. The application has been correctly terminated. In summary, by completely integrating the SITOP PSU8600 power supply in the automation system, the power supply becomes an important module in the digital environment. This is because not only can the power supply system offer more functions and help save energy, but the control circuit becomes even more reliable.